we're going to look at a couple of the practice AP questions for the Chapter 4. And specifically, we're looking at the ones that have to do with the chemical analysis. Now, one thing you want you to notice here is that I have a picture, and this shows how this chemical analysis is done. So we would have something like a H2O absorber, and that might be something like CaCl2.2H2O, some kind of a hydrate, and when the products from the combustion products pass through that absorber, it's going to gain some mass. Then we would have a CO2 absorber, something like maybe calcium oxide, that picks up water and becomes calcium carbonate. And again, if we measure the mass of this before and after, that'll give us the mass of CO2. So in this way, we're going to get some numbers for the H2O that's given off as we burn the hydrocarbon, and also the amount of carbon dioxide that comes off. Now, what we want to do is look at two of the problems. One, the 1991 problem, very straightforward. Now notice what's happening here. It's a hydrocarbon, and a hydrocarbon means a compound that is just made out of hydrogens and carbons. So when we get done, we get a formula that's C and H, and it tells us how much water, how much CO2. So here we have the given 7.2 grams of water, and we're using our molar mass, our heart of the problem, and that just gives us moles of hydrogen, rounding that off to two significant digits. In the same way, we have liters of CO2. Now if we have that, we can use our number here, 22.4 liters per mole. Heart of the problem again. Okay, notice heart of the problem this time is 1 mole of C for 1 mole of CO2. And make a little note, if you look at the answers that I have for this problem, I actually have a 1, which is wrong. I have the correct answer, but I have a 1 written for some reason. So that's a mistake. Then here we get the moles of CO2. So standard situation, the formula is sort of like this. Carbon 0.32, hydrogen 0.80. But of course nobody writes formulas like that, so we divide them both by the smaller number, 0.32, and it comes out to C1H2.5. So we can see, okay, if it's 2.5, let's multiply both of those by 2, and we end up with the final answer, C2H5. So that is our empirical formula, and that's problem 1991. Now, jump to 2001. There was a part A, and I'm not concerned with that. I'm looking at part B, and what I want to do is to add to this part B, okay, and say what would be the empirical formula of this compound. And this is different because now we have a compound that has C and H and O, all three of those in here. Now when we work this by combustion, that means we are mixing our compound with oxygen to burn it, and then we're getting our water and we're getting CO2, but out of those, again, we can only depend on the amount of hydrogen in the water and the amount of carbon in the CO2. We cannot use the numbers for the oxygens for our formula because we don't know if the oxygen comes from the compound or from the oxygen used to burn the hydrocarbon. So we're going to get our oxygen by subtraction. So here's how this problem goes. We start off down here, we have our given, our amount of H2O, molar mass, heart of the problem, and we get our moles of hydrogen. Same thing here, if we can go on one more step and get the grams of hydrogen. So we're using the molar mass of hydrogen, and notice we're using hydrogen atoms because we want to get a formula with the number of atoms. So we have the number of atoms and we have the mass of those atoms, and we're going to use that for subtraction. In the same way, we go back here. Here we have our volume of CO2. We use 22.4 liters per mole, heart of the problem, and we get our moles of carbon. And then we also use our atomic mass of carbon to get the mass of the carbon. Now, let me clean up this page a little bit. And we can move our page here up a little bit and see the rest of these answers. And what we notice now is we have another color. Okay, so we have the moles of hydrogen, moles of carbon. We have the grams of hydrogen and grams of carbon. Well, we know in the problem that there's 3 grams of compound, so we subtract the mass of hydrogen and the mass of carbon, so whatever left must be the mass of oxygen. Now that we know the mass of oxygen, we're going to use our molar mass of oxygen to figure out how many moles of oxygen. And again, notice this is oxygen, which we know is normally diatomic, but for these formulas, this is the one time where we always use the atomic mass, not the molecular mass. So 16 grams per mole. So we have a number for the moles of oxygen. So moles of hydrogen, moles of carbon, moles of oxygen. So we're going to take our formula, and the formula at this point would be C.16607, H.1332, and oxygen 0.0544. And again, nobody writes it that way. So we divide all these numbers by the smallest value, which is the 0.0544, and it comes out to be 3 to 2.45 to 1. Now that's still not going to quite work because it's a 2.45, but that's almost 2.5. So we're going to go ahead and double each of these numbers. So we can see we're going to get a 6, a 5, and a 2. And that leads us to our final formula, C6H5O2, I left off the 2, and that is our empirical formula for this compound. That's it.